Hey Physics 30s, how's it going? So today we're going to talk about, or actually this video, we're just going to talk about diffraction gratings. Um, in Young's dual slit experiment, we had two slits, very small little narrow slits, but light through them, and as long as they're in phase, they created this nice interference pattern. How diffraction gratings work, rather than two slits, it is now just say a piece of material here with thousands of slits all the way down. So it's a diffraction grating. And usually when they say this, they usually talk about, okay, here's the distance. Let's just say that this is 1 centimeter large. Then maybe they'll say that in 1 centimeter, we have 5,000 slits in there. Okay? So that's what a diffraction grating is talking about. They just talk about how many slits they have in a very specific length. When we talk about two slits, we just talked about, okay, here's our two lines, and there's the distance between them. There's only two lines. There's a line here, there's a line here. Now what this is just like a piece of metal, and they just etch a bunch of lines out of it. So you get these really thin lines in it, where light can just pass on through. How this works, and how we're going to work in terms of the math here, we use the exact same equations as Thomas Young's dual slit experiments. So the xd over nl and the lambda is equal to d sine theta over n. But in those formulas, they use the letter d. The d is the distance between the slits. Not how many slits there are, but the distance between them. So we need to figure out, if I'm going to use this formula, I need to figure out how far apart are they? How far apart are these two little slits here? Or each slit, if every slit is evenly displaced, how far apart are they? And once I know how far apart those slits are, then I can use that D to solve that question of the next questions. So the easiest way to do this is think about, okay, rather than think about the distance between the slits, what we're given is the slits for the distance, we just want to flip it over. We just take the reciprocal. So to find the D that we're going to use in our questions, we just take the reciprocal of the number of lines per centimeter, per millimeter, per whatever, right? That distance is just the reciprocal between the two, and then everything else is just mathematically the same. So an example of this would be this next question here. Here they tell us, okay, so we have, now you don't necessarily have 1 centimeter material. You might have like a big chunk of material. They're just telling us that within 1 centimeter of that material, there's 1,000 lines here. So the D value for all the math that we're going to do is just going to be 1 over, there's 1,000 lines per centimeter. Now you take the reciprocal of that, it's going to be 1 over 1,000, and then flips over, it becomes centimeters per lines. All right, so rather than lines per centimeter, now it's centimeters per line. So I can say that this is 1 over 1,000. 0.001 centimeters. Whatever units you start off with is whatever units you get here. Okay? And then everything else is the same. So they tell us that there's a screen, some kind of measuring device that's 4 meters away. So that's my L. The first order bright spot, bright fringe bright spot. That's a N value. So that's the first one. So that's N is equal to 1. So first stands for 1, obviously. And they give us the distance there of 19 centimeters. So I'm just going to change that to meters divided by 100. XD over NL. Uh-oh. Well, if I'm going to try to think about using that other formula, I've got to know what the angle is. So I'm going to go tan theta is equal to X over L. Let's find out what that angle is. I have the X over L right there. Tan inverse, 2 degrees, 2.7 degrees. Now, I think that's too big to ever use that X. So this formula is XD over NL formula. That angle is way too big. I'm just going to cross that off. I'm not going to bother using it because we found the angle. So why not just use the other formula? Just as simple, because once we find the angle, it's in my calculator. Got the angle in my calculator. I'm just going to go D, which we found by taking the reciprocal there. Oop, I got to change it into meters. So this is going to be 0.001 times 10 to the negative 2 meters. Kind of weird notation. That's not scientific notation. Okay. Remember the scientific notation, the first digit has to be significant. In this case, it's not. Times my sine of my angle, which we just found, divided by 1. Oh. Always get these nanometers numbers, which is nice. So it's probably bluish light because it ends up being 4.79 times 10 to the negative 7. Everything seems like 3 sig dig, so 479 nanometers, which is probably bluish. It's getting a bit wide, so maybe it's blue-greenish. Yeah, maybe. So again, so we're not using this formula. It's a bad formula. It's a good formula for specifically test questions where I might just say, what happens if I changed my distance between the slits? What if I changed the wavelength? What would happen to all these numbers up here? Anyway, how many lines per centimeter would a diffraction grating have if the third dark spot, remember we talked about this already, third dark spot, if I were to try to draw that out, n is equal to 0 is my central bright spot, n is equal to 1 is my first bright after that one, so this is my second bright spot. So my third dark spot, so this is my first, second, third, slightly after 2, so it's 2.5. It's located 5 centimeters. Change the meters there. So that's my x from the central antinode. The screen, 60 centimeters, so I'll just go 0.6 centimeters from the grating. And they say you assume our wavelength to be 500. So let's just assume that. What are we looking for here? Well, we need to find D. Where's my D? Again, I got XD over NL. But the problem is I don't know what the angle is, and I think this angle is even worse than the previous ones. It's 4.7, so this is even worse. So I'm thinking, okay, got to find that angle to verify whether or not I can use the other garbage formula, which we're not going to use because we're just going to find the angle anyway. X over L, which we have over here, is 4.736 degrees, sorry, 636 degrees. So we know that. So now what we're going to do is we're going to take that angle, which we just found, and use it in this formula. Yeah, times the n up, divide the sine theta down. We have everything there, so I'm just going to go 2.5 times my wavelength in meters. Not my wavelength, what am I talking about? Yeah, times my wavelength in meters, yes. Let's look at the wrong formula for some reason. Sine my angle, we just found. Anything good in there? So we get a distance between the slits to be 0.001505 meters. It's not asking for that. That's if it was just 2 slits. That's how far apart they would have to be, right? But we have lots of slits. I want to know, say I have a meter's worth of material, actually a centimeter's worth of material. How many lines would be in there? So what I'm going to do first is I'm going to change this to centimeters. Okay, 0.00. What am I talking about? Change it to centimeters. 1,505 centimeters. So times it by 100. Okay. Then what I'm going to do is I'm going to take the reciprocal of this. I'm going to go 1 over this answer to find out how many lines I can fit in 1 centimeter. Okay, 1 over my answer, 6.64 lines per centimeter. Not very much there actually. Just 1 second. All right, so I was looking at it, I was like, that doesn't seem like that much here. We're off by like a factor of 1,000 here. Now, the reason that we're off by a factor of 1,000 is because I forgot to change this into meters properly up here. There's nanometers. So this should be, hello, how's it going? Pretty good. This should be times 10 to the negative 9 right there. So that's going to mess up a lot of my stuff here. So we get the same numbers-ish, but times 10 to the negative 5. Actually, I should probably retype that. Negative 5, and then I'm going to go 1 over this answer, and we're going to get 60 something. Oh, sorry, I went in centimeters, sorry. Oh, let me just retype this in my calculator. I'll be right back. All right, so retyping this back in my calculator here. So this is in meters. I'm going to change that into centimeters by timesing by 100. So you get 0.0015. I'm missing a bunch of zeros there when I did this. 3 centimeters, and then I'm going to go 1 over that answer. Okay, so if I go 1 over this answer, so I'm going to erase this here. I put that in this spot here. Oh, geez, come on, get in my way. Okay, so 1 over that answer. Because it's in centimeters, this is going to be how many lines per centimeter? So it's actually 664 lines per centimeter. I'm sorry about that. Yeah, I just messed up with that 10 times 10 to the negative 7 at the top there. My bad. Yeah, so I'm going to stop this video here, and I'll have another video in the next one here. All right, see you in a bit. Bye.